Hello everyone, today we are going to talk about covariance and correlation. This is slide 11. So far we have talked about measurable locations and measurable variability, right? This was in chapter 3 and this was in chapter 4, right? Now we consider the relationship between the two variables. For example, if I want to know the association between the number of hours I have been studying for my exam and then my score, something like that. I mean, definitely it's gonna look like something like this, right? Um, for example, this is like a number of hours I study for the exam, and this is my score for the exam. So I can ask, students what are your score and how many hours you studied and so far. And each of these points can be coming from one observation. Like this is like a student A, he studied like 5 hours and but got like a 60. But on the other hand, this person studied like 10 hour but got like 75. And so let's say I have 40 observation, something like I can plot each of them. It would look something like this, right? Now I'm gonna just make something like that. So based on this graph, what do you see? So some of you might say, oh, I see some positive association between this number of hours you are studying and score. Yeah, that is correct. Why? Because this is upper sloping. So you can know whether they are positively correlated, or associated between these two variables by looking at some kinds of slope because it's upper sloping. So what you can do is you can draw a line over here, something like that. Then, oh, I know, we know the slope is what? It's rise over ln, right? So the slope is positive. So we can say these are actually positive correlated. I'm gonna more talk about this like a slope things and some kinds of intercepting in chapter 12, but this was the basic idea. So previously, again, we talk about the mean, average, and then average of the score and also variance of these two, etc. But now we're gonna talk about this association between these two. Okay, so open you're gonna see is these two. So first thing is covariance and correlation coefficient and regression. These three are one of the most important part in this statistic course, and also very important if you want to write a paper or write a draft or project, etc., etc. So respected chapters that might help you for your understanding, or if you need some more backgrounds, please try to read this chapter on your textbook, okay? The example is, the example I just gave you, like the association between the scores and number of hours you studied. I had like a 40 observation. I just made up, right? But I can have any kind of relationships. Let's say for 183 countries, I'm gonna I'm gonna analyze the association between temperature and GDP per capita. So my intuition is okay. I mean, how the temperature affects GDP and how they are correlated. This is basically my underlying research question I want to explore. So you might have collected some data. Again, there is like a 183 countries, So this is one of the columns. So column variable is usually variable. And this is a variable number one, and this is variable number two, which is GDP per capita. So I first want to know this kind of association. So, I mean, in this example, I can use only two, but you can use any other thing. For example, this is like education of the country, or this can be whatever value you are interested in. For example, if you want to know the association between education and GDP per capita, you can definitely look up those two association. I mean, I didn't have those one in here, but I'm just saying you can have that, like something like that. Another variable, say, okay, the education of the average education of the people in the country is like I mean, let's say 12 years and 13 years and something, etc., etc., etc. So these are, each column represent again the variables of interest, and you want to know that. And each row is basically observations. So I'm gonna just delete this part. Okay, so scatter plot is like, as I show you, it's one of the good way to see the associations. So for example, this is the average temperature I'm interested in, and I put the GDP per capita on the y-axis. In the chapter 12, what you're gonna learn is usually you're gonna put those explanatory variables, like something you wanna explain for this GDP per capita, you actually put on the x-axis, and something you're gonna call dependent variable, which you want to be explained by the explanatory variable, which is x, usually put y. I'm gonna come back this more in next chapter, but just wanna give you some feedback. So let's say I just plot the scatter plot over here. What do you see in general? I mean, it might not really obvious at glance, but once you have some kinds of a line that can fit this data very well, you might see something like this. Some like basically draw a trend line. As you can see, okay, I can see some negative association between the two. For example, as the average temperature increase, the GDP per capita decrease, something like that. So that is just some conclusion you can get from these two associations, okay? So linear relationship. So basically what I'm gonna talk more is there are a couple of relationships. I mean, the relationship can be linear or it can be non-linear. So let me give you a couple of examples. No, linear relationship is like that. So x is on the x-axis and this is a y-axis. By the way, you can replicate this kind of plot using Excel or R or any kind of a statistical software. So Excel, these are all from Excel, so you can do very easily like this. So we're gonna mainly focus on linear relationship because that is the benchmark. But if you decide to take more advanced statistic, then you're gonna start seeing some nonlinear relationship. So the relationship you can easily identify from the graph. For example, I mean, basically it's a negative relationship like that, and no relationship and positive relationship, right? So you can identify this by looking at this graph, right? So it is very important that you actually start drawing a line or having the scatter plot will give you some kinds of idea what to do with the directional relationship. Okay. Okay. So the strength of the relationship, which do you think has a stronger relationship? The answer is here because that is more around the line you are looking at. For example, even if their slope are the same, oops, this is not the correct. So let's say these two are, let's just copy this one over here. So pretend that these two relationships are the same, but more data are around this line. That means it's a stronger relationship. So, and then covariance. The idea of covariance is like that. So let's say the red line is like your averages. So basically, my example previous case was this was my number of hours you studied for the exam, right? And this is number of scores you are getting. Let's pretend that the average was like, okay, on average, students just study 9.7 hours. This is average. And let's say their average score was some kinds of, let's say, 80. I'm just made up number. Okay, let's pretend this is average. So what you can get from this graph is, okay, what if, association, how do you define the covariance? The covariance is usually defined by something like that. Okay, xi minus x bar and yi minus y bar. What is that meaning? So that is your average. These two are your average, and this is xi yi. In other words, is xi comma yi. I is individuals. So I can be number one, that is observation one. It can be observation two. And let's say we have 40 students in our class, then it's gonna be 40, something like that. So how it's working is, let's just pick up some number, something like over here. Let's say this dude studied like 15 hours of studying and got 85. Let's just imagine a number like that. We said x was what, 9.7. So xi was what, 15. So what we get in the first part is actually 15 minus 9.7, right? Yi is what? I said they are getting 85 and the average was 80. So this was 5.3 and this is 5. So if you multiply, what do you get? It's 26.5, right? So what's important in here is not actually the amount you're getting, but the sign is most important thing. So you're getting positive sign, right? That means actually it's a positive covariance. So basically this is how you get the covariance. But you can calculate whether they have a positive covariance or negative covariance just using like that. So you can get some kinds of other example, something like over here. Let's say you didn't study much. You only studied like let's say 7 hours, but you got 100. So for some reason, so it's outlier. But let's say then it's gonna be 7 hour minus 9.7, which was the average, times 100 minus 80, which was the average, then it's going to be negative 2.7, it's going to be 20. If we multiply, what you're going to get is basically 54, right? But the number doesn't matter. But what matters is this is a negative sign. That is basically negative covariance. The idea was coming from here. Okay, then based on this, so if this is a positive, then it's positive relationship. Negative, then it's a negative relationship. So, okay. Oh, it was my bad. Actually, the thing I show you was not covariance. It's not, I mean, because you need to summate everything up. So it's not technically covariance, but this is like a positive relationship is more accurate word. So this is a negative relationship. In other words, I mean, this might be something misleading. That means if you study less, then you're going to get a high score. So that sometimes happen. So covariance is average of cross product of deviation. What this means is, I mean, this looks something familiar, right? If you go back to the lecture, like I gave you variance and average thing, how I did the variance was what? So basically the variance I gave you was something like that. Okay. The variance was basically, let's say sample variance of x was 1 over n minus 1 because it was a sample, and it was I equal number 1, observation I for n sample, and then xi minus x bar square. That was variance. But covariance, on the other hand, is the association between x and y, two variable. It was only one, so variance. And then equal, same thing, 1 over n minus 1. Same thing over here, I equal 1, and now the difference is xi minus x bar, it was square, but times yi minus y bar. We just explained this part, right? I just had the example, right? But what you need to do is, this is of course sigma. That means it's a summation, right? So you're summating everything. Let's say previously the first dude got like what? What did he get? I forget the number, like a 57. I'm just making a number. Set 57 was the number for from this part. You know, that was I equal 1, and the second part, for example, like this can. I'm just making up again. Xi was, let's say, 12 hours of study and 9.7 and whatever number I'm getting, let's say, and then 90 minus 80, something like that. I don't still get that. So to get 57, okay, 15.4. I'm just gonna make 15.4 hours. I'm just making. Let's say this is observation 1 and got 57, observation 2, negative 50, observation 3, 45, and etc. Let's say the summation of everything divided by n minus 1 of the n observation is like, let's say, 100, something like that. The 100 doesn't mean anything. What matters for covariance is whether this is positive or not. So if this is positive, the summation of all the covariance, I mean, the relationship of each part is positive, then you can say they are positively correlated or they have positive covariance. If negative, then you can say it's negative covariance. So because we are dealing with the sample, so that's why you are dividing n minus 1. So for population covariance, you should use n instead of that. I explained the difference between sample and population in chapter 4. Again, that was the variance. So let's try to do this example. So I mean, this kind of example can potentially be on the exam, okay? So make sure you know how to calculate those, okay? Let's say I want to find the association or covariance between these two. This is my x and y. And how did we do that? This was a formula, keep that in mind, right? And what should you do? First, find the average of x, average of y. What is the average of x and y? So average was 10. Why? Because you add everything. Negative 5 plus 10 plus 25 divided by 3 is 10. And this is basically adding everything and divide by 3. So this was x bar and y bar. Of course, you can do this, right? Just in case if you're still confusing this part, finding average, go back to chapter 3, okay? Then what you need to do is xi minus x bar. That was x was negative 5 and x bar was what, 10, so 15, negative 15, 0, 15. Similarly, you can do yi minus y bar. Y1 is this part, so it's going to be 35,000 minus 30,000, which is 5,000. Multiply these two, it's negative 75,000. Finally, you can add everything up. So this is a summation. And how many observations do we have? 1, 2, 3. But you need to subtract 1 from here. So it should be 2. So it's going to 1,500. I mean, no, 150,000. So what matters for covariance is negative. So basically, that is saying that the association between this temperature and GDP per capita is negative. So for covariance, what matters is the sign. Why do I emphasize the sign? Because in correlation table that I'm going to cover in a bit, then the magnitude matter in correlation coefficient. For covariance, it doesn't matter. I'm going to come back to that part. So let's say these are the 3 observations we had. This one table are created from Excel file. So you can actually replicate the same thing, you know. So you can get a scatter plot and everything in Excel, but you can do in R or other softwares as well. So negative covariance means the trend line is downward sloping. So colder country tend to have a higher GDP per capita. So yeah. Okay, for convenience, let's change the data a little bit. So let's say they are exactly same, but I'm just previous was Celsius, but now it's a Fahrenheit. Nothing has been changed. This was previously 35,000, 40,000, 15,000, but now I just divide by 1,000 because of that. So what is a covariance? So, I mean, do the same thing just as a practice. Answer is -1 at 270. What was the number? It was -1 150,000. So basically, it's huge different. But does the fundamental change at all? No, it hasn't changed at all. Nothing has been changed. The only thing changed was just I changed the unit. I just divide by 1,000. So basically, nothing changed. Nothing should be changed between these two. That's why I said the sign matters for covariance, but the actual measures, values you are getting doesn't matter for covariance. But it's going to be very important for correlation coefficient, which I'm going to cover right now in a bit. So some of the property would be, so this is a formula of how you define how you convert from Celsius to Fahrenheit. So this is Celsius, you multiply 1.8 and plus 32, it's going to be Fahrenheit. This is previously it was 1,000, but the numbers are so big, I just divide by 1,000. So that is a transformation. What we see compared to previous was after the transformation, basically the sign didn't change, but the number changed, right? So the relationship is you just, since you multiply 1.8 and divide by 1,000, so you can do the same thing. Multiply 1.8, divide by 1,000. So how about this 32? It doesn't matter because it's a constant term. Adding this one or subtracting any number doesn't change the association between these two. So one you need to multiply or divide things only matters this covariance. So multiplicative coefficients are preserved, but additive constants have no effects, as I just explained. So these were the associations. So B and D doesn't affect the associations, but this A and C part actually affect the covariance. Now we see some problems. The relationship does not change, the only thing changed was the unit. So covariance captured the direction or the sign of the relationship, right? But the magnitude doesn't mean anything. So we definitely need another measure which we can talk about how strength the relationship, how stronger relationship has comparing to others. So now we're gonna learn about correlation coefficient. So this part, this is a mathematical formula. This is a correlation, so you don't have to know this part, but you need to know this one. Correlation was coming from basically covariance of x and y. Covariance was coming from the previous case, right? I gave you the equation, divided by standard deviation of x times standard deviation of y. The nice thing about this is correlation coefficient is always 100% between -1 and 1. If this is outside of this range, then something is wrong. Your calculation might be wrong. So it's basically like a standardized version of covariance, which now magnitude doesn't matter. So it captured the strength of the relationship as well as the direction. Previously, covariance only captured direction. Also, it's a unit-free. So which one has a much stronger relationship? Previously, we agreed that this has the stronger relationship. So if we actually calculate the correlation, left one is 0.5 and it's 0.9. So as the number is getting closer to the 1, then it has a positive and a stronger relationship. Again, the number is between -1 and 1. So from 0, 0 means it's no relationship at all. But as number is close to this side, then you're going to have a positive but stronger relationship. But this is a negative and stronger relationship as well. So definitely both have a positive relationship without any doubt, but this one has a stronger relationship. This is how we interpret correlation coefficient. This is an example of 1 and -1. In real life, you barely see this kind of example, but still they're gonna have almost perfect correlationship. I mean, for this one is perfect correlation, but because it's 1 or -1. So 0 means no correlationship, either this one or this one, or etc., etc. No correlationship. So let's try to find the correlation coefficient. So previously, we were able to find the standard deviations and then average like that, right? Standard deviation of X is 15, standard deviation Y is like that. So if we are confused this part, go back to the slide 4, I explained in detail. So using this formula, plug in covariance was here, which is coming from the couple slides ago, and plug in standard deviation, etc. You got this one. What can you tell about this? Okay, they have a very strong negative relationship, right? This is what we have seen in previous scatter plot. So let's look at this one. This was a transform data. What is the correlation coefficient? So based on this information, try to get the correlation coefficient. Your answer would be, actually, you're gonna get exactly the same thing. So it doesn't matter whether you change the data set or not, you're gonna get exactly the same correlation coefficient. That is actually one of the most big advantage of correlation coefficient. It has not only the directional relationship, but also the magnitude is captured in the correlation, which covariance didn't have. So that is definitely a plus. So make sure you guys remember this formula, okay? So in the Microsoft Excel, you can use this function or correlation function to get the relationship based on some kinds of data you have, okay? So let's say there are some kinds of, those who took macroeconomics, this is a standard thing we usually talk about. So we can also, if we have the data, we can calculate the covariance and correlation coefficient of this one. So using data and data analysis and covariance, this is a covariance matrix in Microsoft Excel. So you can actually do this exactly same thing in Excel or any other software. If we are using R, it's gonna be super easy. So you can, it's gonna be even simpler than that. You can use either covariance, or you can use COR or any other commands. If you Google, there are tons of method and software in our program. So you can make much beautifuler figure than this one for covariance. So let's talk about, this is an example. So the diagonal terms are variances. It's usually because how you read this kind of table is after you do this covariance. This is a covariance matrix, by the way. We're gonna learn about correlation matrix after this. So covariance, you guys just remember how you get that, right? So that is a relationship between these two. For example, GDP and GDP. What is the relationship between GDP and GDP? That is basically variance, you know. So if you come back to this one, so if you substitute this one, let's say this was covariance of X and Y, what if you change this one to something like this? For example, you change covariance of X comma X. It used to be Y, now X. So mathematically it's n minus 1 summation xi minus x bar, and now it become xi minus x bar, because this is xi minus x bar times xi minus x bar. Basically, that is equivalent to this, which is variance of x. So this is basically variance of x. So in other words, how you read those tables over here is, since you are looking at covariance between GDP and GDP, these diagonal terms are your variances. So I highlighted in red, but this is actual numbers are covariance between these two. For example, IP and UR, the covariance is negative 2.69. Again, the magnitude doesn't matter here because we are dealing with the covariance. What you need to do is this directional relationship. So does that make sense to have a negative relationship? Yes. Or does it make sense to have the positive relationship over here? Yes. Just always, when you get this kind of thing, make sure you look at the sign and check out whether those relationship make sense or not. So that is very important. So these are the example how you look at this, the covariance of GDP and inflation. is here inflation and GDP, which is negative 1.99, etc. So if we want to know, like, for example, a relationship between TR and GDP, you say, oh, there is nothing over here, but you can look at over here, TR and GDP, because they're gonna be the symmetric, that's why it's omitted. So if I want to fill this one, 2.42 to be over here, and then 0.48 to be here, 1.1 to be here, 5.26 is here, etc. It's going to be symmetric. That's why they only show one-sided. Okay, so after looking at that, you see whether those relationships make sense or not, and you can discuss that. So when you want to write a draft based on something, associations, you always care about these signs a lot and see whether they are making sense or not. So now I'm gonna move to, okay, let's say what is the correlation covariance? I mean, coefficient between inflation and UR. Actually, this is a very, very good example. I potentially this is, this kind of thing is very useful because this is like a covariance matrices, and this is a variance. And what is a standard deviation? That is square root of a variance, right? For example, if you want to know the correlation coefficient between inflation and UR, you need to know standard deviation of UR and inflation, right? So this is a variance. So how do you get the standard deviation? Take the square root of it, right? This is standard deviation of UR. Similarly, you can get standard deviation of inflation, etc. And then how do you get the covariance between inflation and UR? Inflation and UR is 0.48, which is over here, and then square root of 8.26 and square root of 2.57. That's why answer should be D. So without using calculator, based on this covariance table, you can get your correlation table like this. So this is a previously used covariance. Now it's going to be correlation. So these are the correlation metrics. Of course, their correlation would be 1, right? The correlation between GDP and GDP would be 1, and IP would be 1, etc. So now the magnitude doesn't matter. Previously was not. So okay, then we can still interpret that the sign didn't change, hasn't been changed yet at all. So basically, you can not only discuss about the magnitude, but also directional relationship in correlation table. So which pair has the strongest negative correlation? Then first find the negative relationship, and which one has most negative one? It's a 0.36, which is IP and UR. So that is how you find. So yeah. And these are another kinds of examples. This is written for A and B, and these are probability. Now we can get those using probabilities. For example, you can get the average of it, which is 20 plus A plus 4 divided by 3, right? So basically, this is expected value. In other words, this is average, right? And 6 plus 10 plus 4 divided by 3, everything is 10. So A minus expected A, this was again average of A, was 10, because 20 minus 10 is A minus 10. 4 minus 10, this is what? 6 minus 10, and 10 minus 10, 14 minus 10. Finally, you multiply them and just add them up, right? This was the covariance, right? But now you multiply, and then you multiply probability over here. That's why you don't divide by n minus 1, because in probability, right, we are weighting this. That is implicitly dividing the numbers, right? So since we are dealing with the probability, we multiply. That means we are technically dividing, but with some kinds of weights. We are heavily divided for the second part and the first and third one, because they might have some more observations. This is how we did with probability, right? If you are just in case confused this part, go back to chapter 3 and 4, right? Okay, or let me know if you have any questions. So, okay. So what would be the variance of these portfolios? For example, say, I mean, we did this one before, right? In chapter 4, so I'm gonna reveal the answer. Variance was like that, right? First, find the expected value of x, which is the average, and take the difference, take the square, multiply probability, boom, 12. This was what we have learned. So we didn't divide by n-1 because we are weighting that. Similarly, that's why we didn't divide anything over here because we were weighting these numbers, right? Okay, so variance is 12. So suppose the sum of a random variable. So these are some of the properties that I want to discuss. Suppose x is a plus b. The average is still a plus b. Let's say the average of a is 10, average of b is 20, and the average of x would be just 10 plus 20. That is simple. So mean is super simple. Variance is a little complicated. Why is the case? Because so something like that. Intuition is coming from here. So we know in algebra this was the relationship, right? So similarly, like a square is like a variance, because if we think this is a variance is like, for example, it's a standard deviation square, right? So basically, so standard deviation of A plus standard deviation B and square. So let's say A is a standard deviation of A, B is a standard deviation of B, and the variance is just squared of it. If you redistribute, you see something like that. Similarly, variance of X is basically, this one is equal to variance of A plus B, right? That is equal basically variance of A plus variance of B plus 2 times covariance of AB. So that was the basic formula. Okay. So standard deviation, you just take the square root of it. So it's nothing hard. Okay, so previously we got this one. So if you are looking for this expected value of x and variance of x, etc., what you can see is the variance is like a 12. So using those formula, so assets having a negative covariance are used to diversify the risk. So I don't know whether you guys have taken any kinds of risk asset kind of management class or any financial courses. More what this literature is saying, if you diversify your portfolio, or given a certain amount, if you buy more number of stocks than others, you know, just putting everything in one stock, you're gonna reduce the risk. So this is kind of important ideas. When there is no risk, this was ideal comparing to this. So no risk diversification occur when this is equal this. So because mathematically this is equal this, right? So no list, this is a little bit advanced topic. That's why I'm moving fast. If you decide you're gonna take any financial course, you're gonna learn more deeply. So this simple relationship is when there is no risk diversification, then this is a result because of this relationship. Because variance of x should be the same, that means if and only if these two are the same. Yeah, this is kind of like important later part. I mean, if you're gonna take financial economics. So correlation was here from previously, and if no risk diversification occurs, then this was the ideal. So correlation of these two are equal. That means if this correlation is 100% or just one perfect correlation, then there is no benefit of diversification. For example, if the stock A increased by 10%, stock B would increase exactly 10%. Or if it decreased 5% and decrease 5%, etc. So in some, risk diversification does not occur when correlation is 1. But other than that, you're gonna have some kinds of diversifications. Okay, you don't have to know this part, but I'm gonna focus on this one, independence. You guys probably remember in the first few chapter 1 and 2, I explained independence. Independence means X doesn't affect Y. The whatever X happened doesn't affect Y. That is basically independent, right? Um, I explained, like, for example, how you define whether they are independence previously was just look at for example, marginal probability of these two, multiplication of that, A and B should equal joint probability of A and B. That was how we define in chapter 2, right? So, but in here, if they are independent, then there is no effect of covariance, it will be zero. That as a result, correlation would be zero. This is basically independence in this context. Um, If this is a case, we know the variance of x, which was here, that was a formula from previous case, is equal to the one below, right? Because the reason why we are getting this one is equal zero. So if this is equal zero, then variance of b is standard deviation square, variance a equals standard deviation a square. So because if they are independent, then this term would equal zero, which is less than this because, right, this square. So that's why standard deviation of x is less than that if they are independent. So even though two assets are independent, there is a risk diversification. So that means even if these two assets are nothing to do with each other, you still get a benefit of risk diversification because standard deviation is less than this summation of these two because of this mathematical part. Okay. Okay, the later part of this I'm gonna skip because it's gonna be more heavily focusing on the financial diversification and financial portfolio thing. I just added for your information for those who are interested in more financial stuff and why this covariance and correlations are important. But if you have any question, just let me know. Otherwise, we're gonna stop the lecture here. Okay, thank you so much.